Okay, welcome. This talk is about effective reinforcement learning through evolutionary surrogate-assisted prescription, or ESP. And this is joint work in evolutionary AI research group at Cognizant, consisting of Olivier Francon, Santiago Gonzalez, Babak Hojat, Elliot Meyerson, Xin Qiu, and Hormuz Sarshad. And also Santiago, as well as myself, we are at the University of Texas at Austin. So let's see. The big problem we are addressing is this. How can we make good decisions? It turns out that organizations today have a lot of data. They collect data on their patients, on customers' shopping behavior, on students, what they learn, what they don't, and many other domains. That's useful because it allows us to predict what patients, customers, students will actually do in different situations. But that by itself, prediction itself, does not help us make better decisions. That learning problem is different. And it is challenging because optimal decisions are not usually known. The domain that where we're making decisions is usually only partially observable. We don't have all the data about the world when we make these decisions, although many factors affect our outcomes of those decisions. And the many variables in the world interact non-linearly. So it's also very difficult to estimate the effects of the combinations. So the standard methods, direct methods like linear programming, has been used for decades, and also gradient descent, which has recently been very popular and very powerful. They are not really effective in this kind of a domain. So instead, what we need to do is search for decision strategies that would work well, observe how well they work, and then reward those decisions and do more of those decisions that seem to correlate with good outcomes. Now, testing strategy, decision strategy candidate is very costly. I mean, if you try to do it in the real world, it may not be feasible. You cannot afford to cause harm to patients, for instance. Or if you're trying to make decisions about controlling a rocket, you can't explode many of those rockets. It becomes a little too expensive. In some cases, there might be simulators of the domain, like automated driving or various machines or so, but they are not always available for complex systems. They are not always accurate in robotics, for instance, or they are simply just very costly to simulate if you try to do that from first principles. So what do we need to do instead? We can build a surrogate model of the world, a predictive model that tells us what would happen in the real world if you applied your decisions to it. What kind of outcomes would we obtain? And then once we have this predictive model, we can use that instead of the real world to find out how well our decision strategies are working. It's still not simple. In order to find those decision strategies, the space is still nonlinear, it's deceptive, it's very large, it's very high dimensional, and it can be multi-objective. So even with the surrogate, we are faced with a very difficult search problem. And it's difficult for instance, kriging or Bayesian parameter optimization, which can only handle about 10, maybe 15 variables. And it's difficult for reinforcement learning as well. The spaces are too large, they're multi-objective, they're nonlinear, so DQN, A3C, or PPO will have a hard time in solving such problems. So here, I would like to build upon the successes of surrogate-assisted evolution. It's been researched for quite a while. The difference here is that we need to actually evolve a strategy, not just do a black box optimization where we find the optimal point using a surrogate of the model. So let's see what we could do about finding a strategy. That's now ESP, the Evolutionary Surrogate-Assisted Prescription. The idea here is to use a neural network to represent a strategy, and then combine that with another neural network, perhaps, that represents the prediction, represents the surrogates. And this is already something that at least pieces of it have been applied to many real-world tasks, and here are two that we've done at Cognizant. The first one is the CyberAg application, where we evolve recipes, growth recipes for agriculture. And that is based on having a predictor model, a surrogate model. So we don't have to plant all the plants. We actually can ask a surrogate how well a recipe might work. And another example is Ascend, which I've already talked about at Gecko before. That is the optimization of web design so that the users who come to the site would be most likely to click on that action button. And there we have a model of the users in order to design the web page. So different users can get different web pages, although that particular application did not have a surrogate. So here we're bringing them together in ESP. This idea that we can look at the situation and decide on actions and evaluate them using a surrogate that evaluates a particular action in a particular context in order to see what the outcomes would be. So that is in a nutshell ESP. Indeed, we've been using it in industrial and business decision making for quite a while, optimizing many decision making strategies. But here today, what we want to do is actually give it a sort of a formal comparison to something that we know already exists. That is the reinforcement learning method. So if we extend this kind of decision making to sequential decision making, where you have to make many decisions before we see what the outcome is, instead of just designing a single recipe or a single web page, you actually need to do it over and over in a dynamic interaction with the environment in order to see how well you do. That's an extension to sequential decision making. And then when we do that, we actually have something to compare with, the reinforcement learning methods. And we compare it in terms of how efficient it is, in terms of samples in the real world, how reliable the learning mechanism is, and how costly and safe it is. And interestingly enough, we discovered something that we did not anticipate would be there. There's a surprising regularization effect, that the strategies we learn are actually automatically regularized, and therefore they generalize well to new situations. Okay, so let's look into the ESP a little bit more in details. This is again a diagram of the components. So there's a context where we make a decision, and a decision means we decide what actions to take. And then once we have context and actions in that context, there are some outcomes, the cost, whether the patient is cured, and so on. It consists of two models, the prescription that comes up with the actions, and then the prediction that gives you the predicted outcomes. So the prescriptor is the new component here. That's the piece that's hard to find because we don't have any knowledge about what the optimal actions are. So that's something that we evolve. We evolve, for instance, a neural network to create those actions for any context that comes in. So it is a model, a prescriptor model, that maps the context to actions. Since optimal actions are not known, we need to evolve it, and then we need to evaluate every candidate during the evolution. So that's why we need the predictor in order to do this quickly and efficiently without having to destroy anything in the real world. So that component, the second component here, is the predictor. And that's something that is relatively straightforward to do. I mean, the organizations should have this kind of data already. Historical data. Given a context where a decision is made and an action, give me an outcome. So that data should be there, and we should be able to use many different approaches to build this predictor. I mean, it could be a neural net, very naturally. It could be a random forest in some other cases if the data is simpler. In principle, it even could be a first principle simulator, or it could be the real world too. But that's not necessarily efficient. So typically in the examples today, I'm going to show you neural nets and random forests in this row. Okay, so now putting this together, we have a diagram of how this works in the world. And in applications, sometimes you only do this once, you go through this loop once, or in some applications when you don't have a whole lot of data to begin with, you may actually be in a continuous loop where you gradually improve over many iterations through this loop. So the standard process is to train the predictor with the real world historical data. We have context, actions, outcomes that have been collected in the past, over the last years maybe, depending on what you're doing. And this is a standard predictor model we trained it with. And then once we have the predictor, we evolve a prescriptor, a population of prescriptors, and find something, one of those that you trust the most, and then that's deployed. That's applied to the real world. So if we have enough data, then we can do it just once. But in some cases we don't. So once we have some prescriptors, we apply them to the world, and we collect the outcomes. And therefore we get more data on context, actions, and outcomes. Now with prescriptions, with actions that are actually useful, that we would like to perform. And therefore we get a better predictor that's more accurate in predicting actions that you might, that are closer to the optimal. And therefore we can do this multiple times, collect more data, get better predictors, and then also better prescriptors. So that's a basic static process, static in the sense that this is not yet a sequential decision task, but this is what you would use to apply to somewhere in, say, business decision making or something that's a design like the web page or maybe a mechanical design. And now when we extend it to sequences, it's pretty much the same process, but now we do actually have to have this loop active and go over it many, many times. And it starts by applying the prescriptors to the model, to the world, sorry. So we start with some initial set of prescriptors that might be randomly designed. That's our population of prescriptors. They are applied to the model, to the world, in order to get this training data. And with that, we start training the predictor. We can't do that very much because it's very expensive, but we have a few cases and we can start training the predictor with those cases, samples rather. And then once we have enough samples, to train the predictor, we use the predictor to evolve more prescriptors. So we started with the random set, and now we're actually evolving them against the predictor. So now they become good at optimization of the behavior given the predictor. And when we do that, we then occasionally deploy some of these prescriptors to the real world in order to get more training data. And now, again, they are more accurate. They are based on actions that you'd like to perform because they are already partially optimal given the current state of the predictor. And once we get more training data that way, we train a better predictor and loop. And this may have to be done many times. We want to still minimize how many times we actually apply the prescriptions in the real world. And there's a little bit of tuning that goes on. How often do you need it? How much training data do you need for the surrogate model in order to get good prescriptors? And this is actually where the really interesting regularization effect comes in. That they don't have to be completely accurate. Predictor does not have to be accurate. Prescriptors don't have to be accurate. You gain a lot of knowledge by learning this incrementally because you are gradually learning more complex behavior while the predictor is getting trained with more competent examples. We'll look at that in a minute. Okay, so that was the application of ESP on sequences. Let's illustrate ESP now in action in an artificial task, function approximation, where it's easy to see what's happening. So in function approximation, we know the ground truth. So given the state, which here is just one variable in X, these are the actions, potential actions that can be performed. They are now variable values in Y. And the optimal actions follow this kind of sinusoidal trajectory here. So given this state, your optimal action is here. Given this state, your optimal action is here. And then in this visualization, we can see a number of different things. We can see, for instance, the predictor's current state in the colored background. And as you can see here, it's not a very good approximation of this, but it's somewhere there. It's not totally bad either. We also see the actual samples that were used to train the predictor. They are the little spheres here, little dots here. So sampling from this space with just a pretty low rate gives us this kind of predictor. Then we also see the current prescriptor. It's this orange line here. So you see that it's sort of approximating at this point a little bit of the optimal prescriptor. Of course, the optimal prescriptor you see here in this dashed blue line. So that's where the orange line wants to go, or we should try to get it to go to approximate that line. And we also see this dotted white line, and that is the prescriptor that would be optimal given the current state of our prediction. And as you can see, that's pretty messed up compared to even the current prescriptor. And that's fascinating, that it's true that there's again a regularization effect. So let's see how that actually works. Here's a little animation that shows you how the predictor and prescriptor learn over time when we are training the predictor. So, okay, so initially the prescriptions are not that great, but they very quickly converge very close to that blue line, where the predictor optimal prescriptions are still pretty far from it. So that is an interesting effect, that the prescriptor itself is closer to the optimum, given that even though it's trained with the predictor whose optimal is not. Let's play that again. So the white line is quite wonky there. It's all over the place, but the prescriptor itself regularizes. It finds a more smooth approximation of the prescriptions, even given an inaccurate predictor. And that's really great. That means that the prediction does not have to be accurate because we have a regularization process going on already, and we can find good solutions that way. And the reason why we have this regularization is that we are not training against just a single predictor, but the predictor is changing. So we get a sample of various predictors. It's almost like ensembling the predictors in order to train the prescriptor. And that's where the generalization and the regularization comes from. Okay, now let's see. Let's look at a little bit the comparison between other learning methods in the same domain. We already saw time course of this learning and a predictor and prescriptor in this domain. And here are a couple of snapshots of direct evolution, where we're doing exactly the same, except that we are evaluating the prescriptors against the ground truth instead of the predictor. And here we have a PPO, a state-of-the-art continuous reinforcement learning method. And here we've spent an order of magnitude more samples on these approaches than we spent on the ESP. And you can see that they are not learning nearly as well. They are kind of trying to approximate, but it's not really a good approximation. And quantitatively, this is what it looks like. ESP learns very fast and very accurately. PPO eventually learns. It takes a lot longer. Direct evolution has a lot harder time. It might eventually learn if you ran it long enough. And this is the regret and the cost of learning, how many mistakes you make. And you can see that it's very low for ESP. And PPO never really catches up, and the direct evolution is even worse. So this suggests that, oh yeah, also the variance is very low, which suggests that learning is reliable. And here, low regret means that the cost of learning is low, as well as it's safe to learn. Now, we can apply that to other tasks. Here's the CartPole task, which is a standard reinforcement learning benchmark. Here, we have the same kind of results. ESP learns fast. It has a low variance compared to direct evolution, PPO, and DQN. And it also has very low regret compared to DQN, PPO, and direct evolution. So that's nice to know. This is a standard benchmark in OpenAI Gym with standard DQN and PPO implementations, and ESP improves them quite a bit. Now, let's look at another surprising result, the regularization through surrogate modeling. Because you might think that surrogate modeling has to be exactly accurate in order for this whole approach to learn. And it turns out it doesn't have to be accurate. And also, it's even better if it's not accurate, because that leads to regularization. So if you think of the domain that might have a very crooked performance characteristics, and our surrogate smooths it out, and that leads to prescriptions that are also smoothed out, and they generalize better to new situations. And that's the idea, and it's surprising. We really thought that we'd be dependent on the accuracy of the predictor, and we are, but it's actually good that it's not exactly accurate because then we get better generalization. So here's another domain where we tested that in particular. This is the Flappy Bird domain, where the goal is to fly through the pipes for 2 minutes without hitting any of them. And interesting enough, the surrogate rewards approximate behaviors early on, so it's easier to learn this task. Whereas direct evolution gets stuck with certain nonlinear interactions and never really actually solves the task. The solution here is about 3,600. That means that you fly through everything. So here we see a quick video of some of the surrogates. Like early on, the surrogates try to just get the bird to fly through any of the pipes. Like right here, it repeats the situation where it's flying through the first pipes. And once it does that, it really tries to refine it by slowing it down. And after that, it's trying to move in multiple pipes so that the bird would take into account going through multiple pipes in the sequence. And then eventually, when it knows how to do it, it actually has an easy case where the pipes are pretty much lining up and it just has to fly through directly. And then after that, it does the prediction. The surrogate presents cases where the pipes actually vary in their location. And from there, it's not that far to actually build a bird that flies really well. Now, this is the real domain, not a surrogate anymore that's displayed. And it's very accurate in its actions. This is beating most humans. I mean, it's very good behavior that's learned in this surrogate optimization manner. Okay, so it never hits a pipe. It gets through the course and is quite good, quite reliable. Okay, so in the future, where this might go is making decision-making not just creative, discovering good strategies that people might miss, but also making it trustworthy. If we want to deploy it in the world, we got to be trustworthy. So there are a couple of things that we would like to do. We can build a scratch pad where a person intervenes here and decides what the actual decision is that's applied to the real world. Now, it means that they might bring in their domain knowledge. They might explore some alternatives and look at the prediction and find out that they can improve upon the automatically decided prediction, and then therefore convince themselves that it's right. But even if they do choose something else, we still get data that improves the predictor. It's just not what the prescriptor provided. Another way we can make this more trustworthy is to add an uncertainty estimator on top of the predictor. So whenever we are creating decisions, we also get an estimate of, well, we always get an estimate of what the outcome is, but also we get an estimate of how what the confidence interval is around those outcomes. Like there's a certain cost, and then we have a 95% confidence interval on that. That already exists. That's called Rio, presented in the iClear this year, and that can be added on the predictor of ESP. And the third component is that we can make these components actually rule-based. So instead of evolving a neural net, we can evolve a rule set, and therefore we can make the prescriptions explainable. Okay, to conclude, ESP, Evolutionary Surrogate-Assisted Prescription, utilizes a surrogate and utilizes evolution in order to do well in reinforcement learning tasks. It's sample efficient, reliable, low cost, and safe. And when we have incomplete learning early on in the predictor, it actually leads to regularization. Both the predictor and the prescriptor have a say in that regularization, and therefore we get improved performance and learning. And in the future, we have plans to make this modifiable, estimate the uncertainty, and explain the decisions. And then if we can do that, we believe that there's a mechanism, an opportunity here for deploying creative, trustworthy decision-making in many areas of the real world, such as healthcare, business, education, and society. Okay, thank you.